concentrations and the aqueous reaction. This chapter is incredibly important because it connects chemistry to real-life process, from the way salt dissolves in water, to how sport drinks are formulated, to how reactions happen inside your own body. We will explore concentration, solubility, electrolytes, precipitation reactions, and how to write molecular, ionic, and non-ionic equations. By the end of this lesson, you will understand not only what happens in an aqueous reaction, but why it happens. So let's begin with the part 1, where we're going to talk about concentration. I will suggest you to watch all the parts of this chapter 5. Let's go. So I will start with something fun, molecular gastronomy. This is a field where chefs use chemistry to transform food texture and create surprising dishes. One of the key reactions used in molecular gastronomy is precipitation. A precipitation reaction happens when the two solutions are mixed and a solid forms. That solid is called a precipitate. Chefs use this principle in a technique called spherification, where liquids are encapsulated into little spheres, like fake caviar. So yes, chemistry is delicious. So let's talk about like this solution and solvent solute. When you dissolve table salt in water, we form a solution, which is a homogeneous mixture. The solvent is the component present in a large amount, while the solute is the substance being dissolved. In this case, if I'm giving the example of salt, would be the salt. So, and water is the solvent we call aqueous solution. Remember last chapter that we represent when you write down an equation and you write down aqueous for aqueous solution. Okay, this is what that means when you have the solvent as water. So solution can be described as dilute or concentrated. A dilute solution has only a small amount of solute compared to the solvent. A concentrate solution has a large amount, and you can see in this draw over here, so the particles here are close to each other compared to those over here. So the dilute solution, the particles will be far away from each other. These terms are qualitative. They give us a general idea, but not exact numbers. So because the solutions are mixed, their composition can vary. To describe them precisely, we use concentration, which tells us how much solute is present relative to the amount of the solvent in the solution. One of the most common ways to express concentration is molarity, represented by capital M. Molarity equals the number of moles of solute and divided by the liters of solution. This is a key conversion factor we'll use throughout chemistry. In this example, we have sodium chloride. So to prepare a 1 molar sodium chloride solution, we measure out 1 mole of sodium chloride. So to measure 1 mole of sodium chloride in the lab, we're going to calculate the molar mass of the sodium chloride. You go to periodic table and put those atomic mass together, and you're going to have 58.44 grams of sodium chloride. And I'm adding here in a balloon of 1000 milliliters or 1 liter. So as soon as I add my solid, which is the sodium chloride, so we're going to add water until the mark. So then we mix it, and we just produce a 1 molar sodium chloride solution. Pretty easy. So using molarity in calculations, we can use it because we use as a conversion factor. For example, here I have 0.500 molar sodium chloride solutions, which contains 0.500 moles of sodium chloride for every liter of solution. So we can use 0.500 moles per liter to convert liters to moles. So the unit we're looking for must be up here. And if you want to convert from mole to liter must be over here. So the unit you want must be up here. Let's test your understanding. So here ask how many moles of solute are required to make 3 liters of a 2 molar solution. So we have the volume. So that means 3 liters over here, right? So let me just erase this because I already have the math for you in a way that you will understand better than my own handwriting. So here I have 3 liters. So I'm gonna use the concentration, the moles per liter, as conversion factor. So what I need is moles, so that's why I use 2 moles per liter, right? So I have the volume over here, and here's the concentration of the solution, 2 molars per liter. So I can cancel out the liters, and I'm gonna have 6 moles of solute. Good? Okay, so let's go in the next one. So if you dissolve with 25 grams of salt and 251 grams of water, what is the mass of the resulting solution? Of course, we need to take in consideration the conservation of mass. If you add both together, you only need to add both together. So 25 plus 20, 251, and you get 276. So there is no magic here, right? One more. One volume of 0.274 molar sodium sulfate solution contains 1.22 moles of sodium sulfate. So here, what we have is the number of moles. So what I'm going to do is here 1.22 moles, right? And I'm going to multiply by my conversion factor because I have the concentration over here, right? So I'm gonna use in this way because what I want is liter, and I want to cancel out these units over here. So if I divide 1.22 by 0.74, I'm gonna have 4.45 liters. So pretty easy, right? So as soon as you learn how to work with the units, you will work so well as stoichiometry and concentrations, because that it's only about how to know how to work with the units, right? So in the dilution, this is something that we always do in lab. And sometimes we need to prepare a more dilute solution from a concentrate stock solution. So, and the key over here is that M1V1 equal M2V2, where M is the mole solute and the solution, and V is the volume of the solution. Okay? So in some books you're gonna read C1V1 equal to C2V2. That is the same thing, that is concentration times V1, concentration 2 times V2. So when you want to make solution of lower concentration from the stock solution, more solvent will be added. And why this work? This work, because what changes over here is only the quantity of the solvent. So if you look at this over here, so I have a cup over here, or beaker, that is 500 milliliters, okay? And here I have a beaker that is double, that is 1000 milliliters. Imagine if I'm adding here 2 moles of glucose, okay? Or sucrose. Okay, so it doesn't matter. So just pay attention to this. So I'm adding 2 moles of glucose over here. and 500 milliliters. Now I'm gonna transfer this 500 milliliters to a beaker of 1000 milliliters, and I will complete 1000 milliliters with water. This is an aqueous solution. What happened over here? I still have 2 moles of glucose. So the quantity of solute is the same. It didn't change at all. What changed was the quantity of solvent. Was the quantity of solvent that I add to make 1000 milliliters over here. So this is why this equation works, because the number of moles will remain the same. The thing that will change is the final concentration, because I'm increasing the quantity of solvent, okay? Because dilution is the process whereby the concentration of a solution is lessened by the addition of solvent, like over here. So if you use the dilution equation, you can calculate that we need 0.150 liters of the 10 molar Stokes solution to produce 3 liters of 0.500 molar calcium chloride. Pretty easy, right? Because you're gonna do is use the Me1V1 equal Me2V2. So I want to produce this 3 liters with 0.500 molars, and what I have is 10 molars, and I need to know what is the volume I need to use to have that concentration over there, right? So what I'm going to do is to grab V1 over here, and it will be 3 liters times 0.500 molar divided by 10 molar, okay? So let me erase this because this looks like I have a 1 over here. It's 0.500, okay? So if you divide this, what you're gonna have is 0.150 liters of the Stokes solution. So then we're gonna add here 0.150 liters of 10 molar Stokes solution, and then you're gonna complete with the water until 3 liters mark. So this is the way you make any dilution. Of course, it's dilution, so we go from the most concentrated to for a lower concentration, okay? So let's test your understanding over here. So the image shown above represents a small volume with 500 milliliters of aqueous ethanol solution. So here is the image. So if I add more water, so if you add an additional 500 milliliters, how do you think that's gonna happen over here? So I will keep the same, however they will be more separate from each other. These look the same. These have more molecules of ethanol, so it doesn't make sense. So this cannot be. These look the same distance from the others, like equal image. So here is showing just a piece of the molecules. However, the molecules are separate from each other, and this is what you're gonna see in this image, because the image with fewer ethanol molecules in the same volume is the most diluted one. So this is why the answer is C. So we have different types of aqueous solution and the solubility. Consider 2 familiar aqueous solutions, salt water and sugar water. Salt water is homogeneous mixture of sodium chloride and water, while sugar water is homogeneous mixture of sucrose and water. As we stir either of these 2 substances into the water, it seems to disappear. How do solids such as salt and sugar dissolve in water? And this is what you're going to discover in the next part of this class. For now, That's it. That's all. Bye for now.